three-phase 208 delta to 120/208Y transformer is generally the more appropriate and efficient solution compared to using multiple single-phase transformers. There are several reasons for this recommendation, including voltage conversion, efficiency, space saving, and load balancing. Firstly, voltage conversion. A three-phase transformer is designed to convert all three phases of a 208 delta supply to the required 120/208Y voltage configuration. This ensures that each of the three phases are properly balanced and that the correct voltage levels are consistently available for all connected loads. Secondly, efficiency. When compared to using multiple single-phase transformers to achieve the same voltage conversion, a single three-phase transformer typically offers greater efficiency. The alternative approach of using single-phase transformers often requires connecting them in parallel to meet the required output capacity. This parallel connection can lead to additional energy losses within the system. These losses can increase operational costs and reduce the overall efficiency of the electrical distribution system. Furthermore, the parallel configuration of multiple single-phase transformers can be more susceptible to voltage imbalances across the phases. Thirdly, space saving. Space constraints are a common consideration in electrical installations. A single three-phase transformer generally occupies less physical space than an equivalent setup using multiple single-phase transformers. This can be particularly advantageous in locations where space is limited, such as in compact electrical rooms or densely populated equipment areas. Reducing the physical footprint of the transformer installation can free up valuable space for other essential equipment or allow for better accessibility within the electrical room. Finally, load balancing is critical for a stable and safe electrical system. A three-phase transformer is designed to distribute the electrical load evenly across all three phases of the system. This balanced distribution minimizes the risk of overloading the neutral conductor. An overloaded neutral conductor can lead to a variety of problems, including increased voltage drop, overheating, and potentially hazardous conditions. By ensuring proper load balancing, a three-phase transformer helps to maintain a stable and reliable power supply for all connected equipment. The use of multiple single-phase transformers to convert 208 delta to 120/208Y is generally not the recommended approach due to the potential for voltage imbalances, reduced efficiency, and safety concerns. It's generally advisable to utilize a three-phase transformer for this type of application to maintain a balanced, efficient, and safe electrical system. Understanding the principles of operation for both delta and Y transformer configurations is essential for effective application. The delta configuration, characterized by its closed loop, provides a high level of reliability. If one transformer within the delta bank fails, the other two can continue to supply 57.7% of the original three-phase capacity in an open delta or open V configuration. However, the delta configuration does not inherently provide a neutral point, which is often required for grounding in single-phase loads. In contrast, the Y configuration features a neutral point, making it suitable for supplying both three-phase and single-phase loads. The Y connection also offers the advantage of a lower voltage to ground, enhancing safety. When selecting a transformer, it is crucial to consider the specific requirements of the application, including voltage levels, load types, and space constraints. Consulting with a qualified electrical engineer or contractor is highly recommended to ensure the selection of the appropriate transformer for the specific application. Additionally, it is important to comply with all applicable electrical codes and standards, such as those outlined by the National Electrical Code, or NEC, to ensure a safe and code-compliant installation. Some additional points for your consideration are as follows. Firstly, harmonics. Nonlinear loads, such as variable frequency drives and electronic equipment, can generate harmonic currents that can negatively impact transformer performance. These harmonic currents can cause increased heating, reduced efficiency, and potential damage to the transformer. To mitigate the effects of harmonics, consider using a transformer specifically designed to handle harmonic loads or implementing harmonic filtering techniques. Secondly, transformer sizing. Proper transformer sizing is critical to ensure reliable operation and prevent premature failure. The transformer should be sized to accommodate the anticipated load, including both present and future demands. Overloading a transformer can lead to overheating, reduced lifespan, and potential safety hazards. It is also important to consider the inrush current associated with certain loads, such as motors and transformers, when determining the appropriate transformer size. Thirdly, transformer protection. Adequate protection devices, such as fuses and circuit breakers, should be installed to protect the transformer from overcurrents and short circuits. These devices should be properly sized and coordinated to provide reliable protection without nuisance tripping. Additionally, surge protection devices may be necessary to protect the transformer from voltage surges caused by lightning or switching events. Fourthly, transformer maintenance. Regular maintenance is essential to ensure the continued reliable operation of the transformer. This includes periodic inspections to check for signs of damage, overheating, or oil leaks. Transformer oil samples should be taken and analyzed to assess the condition of the oil and identify any potential problems. Additionally, the transformer bushings and connections should be inspected and tightened as necessary. Fifthly, energy efficiency. Energy-efficient transformers can significantly reduce energy consumption and operating costs. Look for transformers that meet or exceed industry standards for energy efficiency, such as those established by the Department of Energy, or DOE. Investing in energy-efficient transformers can result in significant cost savings over the lifespan of the equipment. Sixthly, environmental considerations. Transformers can contain materials that are harmful to the environment, such as oil and polychlorinated biphenyls, or PCBs. It is important to handle and dispose of transformers properly to minimize environmental impact. Consider using dry-type transformers, which do not contain oil, in environmentally sensitive areas. Seventhly, NEC compliance. All transformer installations must comply with the applicable requirements of the NEC. This includes requirements for grounding, overcurrent protection, and wiring methods. It is essential to consult with a qualified electrical inspector to ensure compliance with all applicable codes and regulations. Eighthly, documentation. Maintaining accurate and up-to-date documentation for all transformer installations is essential for troubleshooting and maintenance purposes. This documentation should include transformer nameplate data, wiring diagrams, and maintenance records. Proper documentation can save time and money when diagnosing and repairing transformer problems. Ninthly, safety precautions. Working with transformers can be dangerous due to the high voltages involved. It is essential to follow all applicable safety precautions when installing, maintaining, or troubleshooting transformers. This includes wearing appropriate personal protective equipment, or PPE, and energizing the transformer before performing any work. Tenthly, grounding. Proper grounding is critical for the safe and reliable operation of transformers. The transformer must be grounded in accordance with the requirements of the NEC. This includes grounding the transformer enclosure, the neutral point of the Y-connected secondary, and any exposed metal parts. Effective grounding helps to minimize the risk of electric shock and equipment damage. As an example, to comply with the 2017 NEC, you could review a few sections. For example, consider NEC Section 450.3, which pertains to overcurrent protection for transformers. This section provides detailed requirements for protecting transformers from overcurrents, including both primary and secondary protection. The specific requirements vary depending on the transformer's voltage rating and impedance. Another example is NEC Section 450.11, which focuses on transformer grounding. This section outlines the requirements for grounding transformer enclosures and secondary systems. Proper grounding is essential for safety and to minimize the risk of electric shock. For another example, consider NEC Table 450.3b, which provides guidance on selecting overcurrent protection devices for transformers rated over 600 volts. The table specifies the maximum allowable overcurrent protection device rating based on the transformer's impedance and primary voltage. These are just a few examples, and there are many other relevant sections of the NEC that may apply to transformer installations. It is essential to consult the NEC and other applicable codes and standards to ensure a safe and code-compliant installation. Let's delve into each of these NEC sections a little further. Firstly, NEC section 450.3, overcurrent protection. This is a critical aspect of transformer safety and code compliance. The NEC mandates that transformers be protected from overcurrents to prevent damage to the transformer itself and to minimize the risk of fire or other hazards. The specific requirements for overcurrent protection vary depending on several factors, including the transformer's voltage rating, impedance, and whether it's a primary or secondary protection scenario. For transformers rated over 600 volts, the overcurrent protection requirements are generally more stringent than those for transformers rated 600 volts or less. This is because higher voltage systems pose a greater risk of arc flash and other electrical hazards. The NEC provides specific tables and guidelines for selecting the appropriate overcurrent protection devices, such as fuses or circuit breakers, based on the transformer's characteristics. These tables typically specify the maximum allowable overcurrent protection device rating as a percentage of the transformer's rated current. It's important to note that the overcurrent protection device must be sized appropriately to protect the transformer from both overload and short circuit conditions. Overload protection is intended to prevent the transformer from overheating due to excessive load current, while short circuit protection is designed to quickly interrupt the current flow in the event of a fault. Secondly, NEC section 450.11, grounding. Grounding is another essential aspect of transformer safety and code compliance. The NEC requires that transformer enclosures and secondary systems be properly grounded to provide a low impedance path for fault currents to return to the source. This helps to minimize the risk of electric shock and to ensure that overcurrent protection devices operate correctly in the event of a fault. The specific grounding requirements vary depending on the type of transformer and the type of secondary system. For example, a separately derived system, such as a transformer that supplies power to a separate building or structure, must be grounded in accordance with specific rules outlined in the NEC. These rules typically require the installation of a grounding electrode conductor which connects the transformer's neutral point to a grounding electrode, such as a ground rod or a metal water pipe. In addition to grounding the transformer's secondary system, the NEC also requires that the transformer enclosure be grounded. This is typically accomplished by connecting a grounding conductor from the enclosure to the building's grounding system. Thirdly, NEC Table 450.3b. This table provides specific guidance on selecting overcurrent protection devices for transformers rated over 600 volts. The table specifies the maximum allowable overcurrent protection device rating as a percentage of the transformer's rated current based on the transformer's impedance and primary voltage. The impedance of a transformer is a measure of its opposition to the flow of alternating current. Transformers with lower impedance values typically require higher overcurrent protection device ratings than transformers with higher impedance values. This is because transformers with lower impedance values can deliver higher fault currents, which can quickly damage the transformer if not properly protected. The primary voltage of a transformer also affects the overcurrent protection requirements. Transformers with higher primary voltages typically require higher overcurrent protection device ratings than transformers with lower primary voltages. This is because higher voltage systems generally have higher available fault currents. In addition to these specific NEC sections and tables, there are many other relevant requirements that may apply to transformer installations. It is essential to consult the NEC and other applicable codes and standards to ensure a safe and code-compliant installation. This may involve working with a qualified electrical engineer or contractor to design and install the transformer system. It is also important to obtain the necessary permits and inspections from the local electrical authority. Ultimately, the goal is to ensure that the transformer installation is safe, reliable, and compliant with all applicable regulations.